Alright, this is exam 3 and I am Dalton Harris. The problem is chapter 3, problem 19. Find the necessary and sufficient condition on the real number b greater than 1 such that the floor of log base b x is equal to the floor log base b floor of x for all real x is greater than or equal to 1. So essentially what we're doing is we're trying to find a condition that holds true that would keep this equation true. First thing we're going to do is define some key elements. Real number, referenced twice here, is a value of continuous quantity that can represent a distance along a line. In other words, any number, regardless of if it's a decimal fraction or a whole number. An integer, however, is a number that is only a whole number, and it can't be written with a fractional component or with decimals. The floor function, which is going to be used this entire time, is this is the literal definition of it, but it's literally just a rounding feature or function. So if you have 10.5, if you floor it, you round down. The inverse of flooring is actually called ceiling. Not that you need to know that, but it's handy to know. Logarithm. This is also going to be used this entire time. So logarithm is basically how you find the what the exponent is going to be of this base. So when you have x or log base x y equals z, in order to solve for z or any of these, you would raise x to the z equals y. First thing I noticed when I read this question was that it referenced real numbers twice, and to me that implies that in order to find this sufficient condition, I'm going to need to dip into the decimal pool. So I took a more trial and error approach to solving this problem. We'll start with the basics of log base 2 equals log base 2 1 equals log base 2 floor of 1, which holds true because 0 equals 0. This is where the clue of real numbers kind of came into play for me. Since b is greater than 1, I decided to make b 1.5 because that's also real, and decided to keep x equal to 1 just to keep it simple. This gives me this equation, which again gives me 0 equals 0 because anything with a 1 here is going to be 0. Now what if we used a value for b and x that I know will give me a value greater than 1 that will also force me to apply the floor function? So we're going to keep b as 1.5 for the sake of being consistent, and we're going to let x equal 2 because this will give us a number that's greater than 0, and it will also force us to use this floor function because 1.5 raised to some decimal will only give us 2. So now this is our equation, and what we get is 1.70951 equals this. So now again we have 1 equals 1. One of the more helpful clues is also in the original equation. Notice the floor functions in this equation here. The left side, the entire thing is floored. Right side, it's also true. However, the x is also floored on the right side. This means that if we set our x equal to 1.5, the left side, it'll still be 1.5. But on the right side, if we floor that 1.5, it'll go down to a 1. So that's exactly what we're going to try. We're going to set x equal to 1.5. So this is the new equation we get. And notice it's still floored. So log base 1.5, 1.5, the answer is just going to be 1 over here. And obviously if you want to get 1, you just need to raise anything to the exponent of 0 and you'll get it. And don't forget that 1 came because we floored this. So now we have our exception to the original equation. Now we just need to find a condition which will make this exception not be an issue. So now we're in the final steps, the home stretch of the problem. Given what is known about logarithmic functions, when you have log base b x and b equals x, the answer will always be 1 because b raised to 1 will always give you x given that they're the same. Remember how earlier it said that b greater than 1 was a real number? Well, what if b was not only a real number but an integer? I actually got this idea from going back and seeing if I missed anything in the beginning of the chapter relating to logarithmic functions, and I noticed that the title of the chapter was integer functions, and I was like, what if what I thought about it having to be a real number was not true, and it must be an integer? So that's where I got this logic from. So the new function we're going to go with is this right here. The reason I made b equal 2 is because b greater than 1 and 2 is because b has to be greater than 1 and 2 is the next integer that is greater than 1 because remember integers can't be decimals. So that's the logic I went with. So floor of log base 2, 1.5 equal to, we're going to see if this is actually true. So the left-hand side will turn into 0.58496. And if you remember when we have that floor function, again, you just round down. No matter how high the number is, you round down. Is equal to 0 on the right-hand side, which obviously 0 is equal to 0. That's a good sign, but never know until you try everything, right? So we're going to let b equal 3 because that's obviously the next integer after 2. And we're going to let x equal something that will give us an answer greater than 0 because I just don't like working with zeros. But we're also going to keep it a real number, preferably a decimal. So what we're going to do is make x equal to 10.5 because that's a ugly number, but it's also going to give us something that's not 0. So log base 3, floor of log base 3, 10.5 equal to this on the right-hand side. What we end up getting, the left-hand side will turn into 2.14031. Remember, we floor that, so that'll round down to 2. The right side gives us 2.09590. Again, we're flooring that, because remember this 10 turns into 10, I'm sorry, this 10.5 turns into just 10, and that's why it's less than this on the left-hand side. So we'll have 2 is equal to 2. So now we kind of have a pattern. So what we know, the conditions that will make this equation false, it appears that when b equals x and b is also not an integer, the equation doesn't hold true. So that kind of scratches our b greater than 1 for all real numbers thing that they first gave us. So a wild example is this. I didn't necessarily pull this number out of thin air, but anyways, log base pi. If you enter this entire thing, you will get 1, the floor of 1 on this left-hand side equals 0.95 on this right-hand side. Well, obviously, if you floor this right-hand side, this will turn into 3. That's where that 0.95 comes from. Now, if you floor the 1, you'll just get 1. If you floor 0.95, you'll get a 0. So 1 does not equal 0. So this kind of scratches this first part of the given condition that they gave us, where b is greater than 1 on all real numbers. But the condition that we did discover was that b must be an integer because the equation is false when b equals to x and b is any real number. This is where we got this, where b equals x and b is a real number, including decimals. It just doesn't work because obviously 1 does not equal 0. So the answer to the problem is the new condition that we have is if and only if b is an integer and x is greater than or equal to 1 on all real numbers. Hopefully you learned something, and thank you for watching.